These are notes for AP Calculus AB. This is 9.2, and we'll be integrating back to the inverse trig functions. So there's 3 formulas here that you'll need, just like 3 from yesterday. Each one is integrating back to either inverse sine, tangent, or secant. As with all integration, you typically have the u substitution in place, so you're going to see that here. And instead of a 1, you're going to see an a value. You'll see how that works out, but you'll remember the case from yesterday where we had x over 2, and it led to a lot more simplifying than the previous examples had, and it changed our 1 to a 4, and that's why there's an a here, because a is not necessarily always going to be 1, but if it is, our formulas will just work that out. So you can see this little piece in the formula here, u divided by a, 1 over a, u over a, 1 over a, u over a. Only arctangent and arcsecant have the 1 over a coefficient. They all have u over a plus c, of course, for indefinite integrals. A is just that constant number. We're not going to worry about arc cosine, arc cotangent, arc cosecant. If there is a negative, you'll just pull it out front as a coefficient with any other coefficient you might have, and then you'll just utilize these 3 formulas. So we're going to practice some example problems with these formulas. And you'll notice they're set up like fractions. So this is just another type of integrating a fraction example that we've been working with. We had lots of rules for that in Unit 8. If the numerator was a higher power, the denominator was a higher power, and all that. So you'll see on these, if you try to apply those rules, how they're just different. So number 1 starts this way. So you can see you have several terms in the denominator. If you let u equal 2 plus 9x squared, the derivative of that is 18x, and there's no x in the numerator. So while we do have a higher power in the denominator, u substitution for the entire thing just won't work. So the reason is it's one of these formulas here. So what we want to do is, like when you were practicing difference of squares factoring when you were younger, you started by figuring out what term on each was being squared to make these 2 values. So a is the number piece, u is the variable piece. So we want to do our substitution for both things, and then substitute back in at the end. So here we'll have a is the number being squared. So root 2 is squared to make 2. So a squared, root 2 squared is 2. Over here, the value being squared would be 3x. So u squared, 3x squared is 9x squared. So just with all u substitution, once you identify u, you'll take your derivative there to get 3 dx. You'll notice there is no 3 coefficient, so 1/3 du is equal to dx. And now we want to rewrite our integral with our substitution. So we'll have our 1 over, and we want to write a squared plus u squared. So a squared plus u squared. And then dx is replaced with 1/3 du. So we're going to pull that 1/3 out front and leave du here. So it should look exactly like our formula here. So from here, we'll integrate by keeping our 1/3 coefficient. Now, because this is arctangent, we have to remember that arctangent starts off with a leading coefficient of 1 over a in our formula. So we have 1 over a arctangent of u over a, u divided by a plus c. From here, you'll just make your substitutions back in. So a is root 2, 1 over 3 root 2. Arctangent of u over a, so 3x over root 2. And then plus c. All right, and that's all we do. So if it helps, you can keep going with the u substitution and the a substitution and using it to write your formula. If you're comfortable with it, you can plug in the numbers as you go. All right. So trouble recognizing the difference between arcsine and arcsecant because they both have the square root in the denominator. Sometimes if there's a variable on the outside, it's likely that you're working with arcsecant, but not every time. What you'll want to verify is the pattern. Remember that with arcsecant, you want the variable minus the constant. Arcsine is the constant minus the variable. They always go in that order. So just because I'm starting with the variable minus the constant, that is telling me that this is arcsecant. Rather than guessing that it might be, I can tell that it is from the inside here. So I want to have it set up in this way. So I'm going to find my u value and the a value. So here, u is 2x, a is 3. As with my u substitution, du is 2 times dx. Okay. Now, I want to be careful real quick because when I do my substitution into the formula for arcsecant, I want to have it written this way, 1 over u root u squared minus a squared. This is weird, we don't always do this, but we want a u here and we want u here. We don't usually plug in u substitution in more than one spot. This is the first time that we've done that. So I actually want to write the outside here as my u value. So you'll remember in this case, we just identified u as 2x. So inside I'll have u squared, but outside I need to have u. So this is supposed to be 2x. Well, if I multiply the bottom by 2, I would also have to multiply the top by 2, and this now balances the expression. So this works for me because notice when I took the derivative here, we got 2 dx. I now have 2 dx, and this matches perfectly. So we'll go ahead and rewrite it. So 2 dx in the numerator here is equal to just 1 du. So 1 du. And then in my denominator, this 2x is also u. So you actually plug it in both spots. So you're going to have u on the outside times the square root of u squared minus a squared. So it should look exactly like your formula. Right? And this one is one that sometimes takes getting used to. So you'll practice that. Here, we just want to go ahead and start using our formula. So notice I didn't have any new coefficient like we did last time, so we'll just start how it is with a 1 over a. So 1 over 3 arcsecant of u over a, so that would be 2x over 3, and then plus c. So like I said, you can skip this step and just plug in the values for u and a as you go. All right. Number 3, cosine over sine squared plus 1. So that doesn't simplify, although you might want it to. Instead, we're going to look at using our inverse trig. So which one would this be? Without a square root in the denominator, it's going to be arctangent again. So we're looking for u squared plus a squared. So u is what is being squared, so sine. And then over here, a is just 1. So that's always nice. So remember, whatever your u substitution is, you want to find the derivative. Derivative of sine is cosine, and then we'll multiply by dx. That matches exactly with what we have here, and we're ready to do our substitution. So cosine dx is replaced with 1 du. And in the denominator, I have u squared plus a squared. So my formula said a squared plus u squared, but because it's addition, which is commutative, it can be written either way. And we're ready to integrate. So we'll use our formula, 1 over a, which is 1. Arctangent of u over a, so sine x over 1 plus c. Now that's just arctangent of sine plus c. Okay. So number 4, in order to use the inverse trig functions, we typically just want a constant in the numerator unless our u substitution somehow takes care of any variable. Like in number 3, we took care of cosine and it became a 1. So right now with the square root here, it's not arctangent because it's a squared minus u squared. This is going to be arcsine. So notice a is 2 and u is just x. Now typically when u is just x, it's not really doing anything. Du is just dx, that takes care of this. You'll notice nothing takes the place of this x here. So I could write it as u plus 3, but that doesn't help because the arcsine formula says that you have to have a 1 or a constant in the numerator, not a variable. So there's actually a trick with this one. You're going to split up the sum with the common denominator. So we're going to write it as 2 separate integrals. So we'll have x over root 4 minus x squared dx plus 3 over root 4 minus x squared dx. So this one over here with the constant on top, that will be our inverse trig formula. This one over here with x on top is not inverse trig. So because there's a variable on the top that we can't replace, instead we can't use the u substitution this way on this part of the problem. We have to use the u substitution differently. So this is actually a problem that you would have seen before this unit. And so any idea on what u substitution you might have used? You would let u equal all the stuff under the square root. So we're going to let u equal 4 minus x squared, and that will become the square root of u. And it just becomes one term. So this is u. The derivative there is negative 2x dx. Now you'll notice, because u is not just x, but because it's the x squared, your derivative contains the x for your substitution. So we'll divide the negative 2 over. and then we'll use this substitution into this part of the integral. So we have -1/2 of 1 over square root u, which we'll write as u to the power -1/2 du. This one, we'll use the formula for our inverse trig, and we'll make the substitution that way. So over here, you'll take out the 3. You'll leave 1. And we'll plug in our substitution. So from here, we have 2 for a. A is 2, so this is 2 squared, or a squared. And if you prefer to write 2 squared rather than a squared, you can, minus u squared. Dx is replaced by du, and that's it. This is the formula here. So we want to integrate each of these two pieces. So the first one we integrate, we keep our -1/2 coefficient. We add 1 to our exponent here, u to the 1/2 times 2. We keep going, plus 3 times. We integrate here, which is our inverse sign, which does not start with a 1 over a coefficient. So we jump right into arc sine of u over a plus c. So be careful with the double u substitution, right? One of them is for minus x squared. The other one is a substitute for x. So in our final step, we have negative here. This one is 4 minus x squared to the power 1/2. So root 4 minus x squared plus 3 arc sine of x over 2 plus c. That is not a common problem that you would see on the AP exam or anything, but you might see 1 or 2 of them in the homework, and it's just a really good practice problem. That is the end of the 9.2 notes.